Good morning, students. Now we are going to see the second topic in mechanical energy based processes, water jet machining, which is called WJM. The principle of water jet machining is when high velocity of water jet comes out of the nozzle and strikes the material, its kinetic energy gets converted into pressure energy inducing a high stress in the work material. When this stress exceeds the ultimate shear stress of the material, small chips of the material got loosened and fresh surface is exposed, used to cut paper boards, plastics, woods, fiber, glasses. Now we will see the schematic diagram of the WJM, which is called water jet machining. First one is reservoir, second pump, third is intensifier, fourth is accumulator. Next one is control valve, flow regulator, nozzle, and workpiece. Now we will see the construction and working. It consists of pump, accumulator, control valve, regulating chamber, nozzle, etc. A pump or intensifier is used to raise the pressure of the water. Pressure normally used in the system or in the range of 1500 to 4000 Newton per mm square. Since the cutting action may not be continuous, the accumulator is used to store the water and also it helps in eliminating pulsation. Nozzle is used to increase the velocity of the water jet. The nozzle is made up of sintered diamond, tungsten carbide or synthetic sapphire. The exit diameter of the nozzle is in the range of 0.05 to 0.35 mm and the exit velocity of the water jets from the nozzle varies up to 920 meter per second. A regulating chamber is incorporated in the line to control the flow of water jet to the nozzle. Now we will see the working principles. The working principle of the water jet machining is very similar to that of a abrasive jet machining. A pump or intensifier is used to increase the pressure of the water and the water passes on the accumulator from the pump. Water under pressure from a hydraulic accumulator is passed through the orifice of a nozzle to increase its velocity. When the high velocity of water jet comes out of the nozzle and strikes the work material, its kinetic energy is converted into pressure energy, including high stresses in the work material. When the induced stress exceeds the ultimate shear stress of the material, small chips of the material get loosened and fresh surface is exposed. Now we will see the process parameters of the water jet machining. The main process parameter is material removal rate, geometry and surface finish of work material, wear rate of nozzles. Material removal rate formula is MRR is directly proportional to diameter into fluid pressure. Geometry and surface finish of the work material. The geometry and surface finish of work material mainly depends upon the following parameters: nozzle design, jet velocity, cutting speed, depth of cut, and properties of the material to be machined. Next, third is wear rate of the nozzle. Nozzle wear rate depends upon the following factors: hardness of the nozzle material, pressure of the jet, velocity of the jet, and nozzle design. Next one is advantages. In WJM process, water is used to energy transfer medium. It is cheap, non-toxic and easy to dispose. Low operating cost, low maintenance cost, the work area remains clean and dust free. Very less amount of heat is generated during cutting operation. So there is no thermal damage to the work, easily automated. Disadvantages of a water jet machining. Initial cost is high, noisy operation, difficult to machine odd materials. Applications. This process is very convenient for cutting relatively soft and non-metallic materials like paperboards, plastics, woods, rubbers, leathers, fiberglasses, etc. It can be used to cut intricate contours. Characteristics. Characteristics of WJM. Work material. Soft and non-metallic material like paperboards, wood, plastic, rubber, etc. Tool. Water or water weight additives. Additives. Glycerin, polyethylene oxide. Pressure of water 100 to 1000 megapascals. Mass flow rate 8 liters per minute. Power 45 kilowatts. MRR mass flow rate, MRR material removal rate 0.6 mm cube per second. Feed rate 1 to 4 mm per second. Nozzle material tungsten carbide, synthetic sapphire, standoff distance 2 to 50 mm. Now we are going to see the last topic in mechanical energy based processes, ultrasonic machining process, which is called USM. Now we will be see the basics of ultrasonic machining. Ultrasonic machining is one kind of a grinding method. It is also known as a ultrasonic grinding or impact grinding. The term ultrasonic refers to wave of high frequency. Human ear can hear the sound waves between 20 Hz to 20 kHz. This range is known as audible range. The sound wave which have frequency less than the audible range are called infrasonic waves. The sonic wave having frequency above the audible range are known as ultrasonic waves. The ultrasonic machining process is suitable only for hard and brittle material like carbide, glass, ceramics, silicons, precious stones, germanium, titanium, tungsten, tool material, die, steel, etc. Now we will see the principle of ultrasonic machining process. In this machining method, a slurry of a small abrasive particles are forced against the workpiece by means of a vibrating tool, and it causes the removal of metal from the workpiece in the form of extremely small chips. And it is also known as ultrasonic grinding or impact grinding. Constructions and working. Construction. The general arrangement of ultrasonic machining is this is the general constructions of a ultrasonic machining. It consists of abrasive slurries, workpiece, fixture, tables, cutting tools, circulating pumps, reservoirs, ultrasonic oscillators, lathes, exciting coil, feed mechanism, ultrasonic transducer, transducer cone, connecting body, and tool holder. The ultrasonic oscillator and amplifier, also known as generator, is used to convert the applied electrical energy at low frequency to high frequency. The transducer is made up of magnetostrictive material and consists of a stack of nickel lamination that are wound with foil. The function of the transducer is to convert the electrical energy into mechanical energy. Generally, tough and ductile tools material is used in the process. Low carbon steels and stainless steels are commonly used as a tool material. The tool is braced, soldered, or fastened mechanically to the transducer through a tool holder. Generally, tool holder is a cylindrical or a conical in shape. The material used for tool holder are titanium alloys, monel, aluminum, stainless steel, etc. An abrasive slurry, usually a mixture of abrasive grains and water of a definite proportion, 20 to 30%, is made to flow under pressure through the gap between tool and workpiece. The gap between the tool and workpiece is of the order 0.02 to 0.1 mm. The most commonly used abrasives are boron carbide B46, silicon carbide S1 sorry SiC, aluminum oxide Al2O3, and diamond. Boron carbide is most commonly used abrasive slurry since it has the fast cutting abrasive property. Now we will see the working. Now we will see the working of the unconventional machining process. In that ultrasonic machining, electric power is given to the ultrasonic oscillator, and this oscillator converts the electric energy at low frequency to high frequency 20 kilohertz. The high frequency power 20 kilohertz from oscillator is supplied to the transducer. The function of the transducer is to convert the electrical energy into mechanical vibration. The transducer is made up of magnetostrictive material which is excited by flowing high frequency electric current, and this result results in the generation of mechanical vibration. The vibration are generated in the transducers of the order of 20 kilohertz to 30 kilohertz, and hence ultrasonic waves are produced. These vibrations are then transmitted to the cutting tool through transducer cone, connecting body, and tool holder. This makes the tool to vibrate in longitudinal direction as shown in figure. Abrasive slurries is pumped from the reservoir and it is made up of flow under pressure through the gap between tool and workpiece. In an abrasive slurry, when the cutting tool vibrates at high frequency, it leads in the removal of metal from the workpiece. The impact force arises out from the vibration of a tool end and the flow of slurry through the workpiece. Tool gap causes thousands of microscopic grains to remove the workpiece material by abrasion. A refrigerator cooling system is used to cool the abrasive slurries to a temperature of 5 to 6 degrees Celsius. The ultrasonic machining process is a copying process in which the shape of the cutting tool is same as that of the cavity produced. Normally the transducer used in this type is magnetization transducer and piezo transducers. The various process parameters used in ultrasonic machining is material removal rate, tool material, work material, surface finish, tool wear, abrasive materials, and abrasive slurries. When we compare to a metal removal rate, we should consider a grain size of abrasive materials concentration of slurries, amplitude of vibration, frequency of ultrasonic vibration. What is wear ratio? Volume of material removed from the work divided by volume of material eroded from the tool. First, we will see about a material removal rate. Material removal rate means how much material will be removed per second. Next is tool material used in ultrasonic machining. Generally, tough and ductile tool material is used in USM process. Low carbon steel and stainless steel are commonly used as a tool material. Since very long tools cause overstress, the tool should be short and rigid. Hollow tool can be made with wall thickness greater than 0.5 to 0.8 mm. Side clearance to the tool is of the order of 0.06 mm to 0.36 mm, depending on the grain size of the abrasives. Abrasive materials and abrasive slurries. The most commonly used abrasives are boron carbide, silicon carbide, aluminum oxide, and diamond. Boron is most expensive abrasive materials, and it is best suited for the cutting of a tungsten carbide, tool steels, etc. Aluminum oxide is the softest abrasives, and it is used for machining glasses and ceramics. Material removal rate and surface finish are greatly influenced to the grit or grit size of the abrasive. For rough work operation, grit size of 200 to 400 are used, and for finishing operation, grit size is 800 to 1000 are used. Surface finish. The maximum speed of a penetration is soft and brittle material such as soft ceramics or of the order of 200 mm per minute. Penetration rate is lower for hard and tough material. Accuracy of this material is plus or minus 0.006 mm and surface finish up to 0.0 to 0.8 micron values can be achieved. Work material. Hard and brittle material, non-metals like glass, ceramics, etc. and semiconductors are used as a work material in USM process. Wear ratio, average, penetration rate and maximum machining area of the different workpiece material are shown. And various characteristics of a ultrasonic machining process is abrasives, as I already mentioned, boron carbide, silicon carbide, diamond, aluminum oxide. Abrasive slurries, abrasive grains plus water, 20 to 30%. Vibration frequency, 20 to 30 kilohertz. Amplitude, 25 to 100 microns. Wear ratio, 1.5 is to 1 for tungsten carbide, 100 is to 1 for glass, 50 is to 1 for quartz, 75 is to 1 for ceramics, 1 is to 1 for steel. Tool material, low carbon steel, stainless steel, work material, stainless steel. Work material, tungsten carbide, germanium, glass, quartz. Surface finish, 0.2 to 0.7 mm. Advantages. Extremely hard and brittle material can be machined easily. Noiseless operation. Cost of metal removal is low. No heat generation on this process. Equipment are safe to operate. No conductive materials can be easily machined. High accuracy and good surface finish can be easily obtained. The machined workpiece are free of stresses. Disadvantages of a ultrasonic machining process. Material removal rate is slow. Softer material are difficult to machine. Wear rate of tool is high. Initial setup cost is high. High power consumption. Tool cost is high. Abrasive should be replaced periodically. Applications of ultrasonic machining process. Hole as small as 0.1 mm can be drilled. Precious and intricate shaped article can be machined. It has been efficiently applied to machine glass, ceramics, tungsten, precision mineral stones, etc. It is used for making tungsten carbide and diameter dies, drawing dies, and dies for forging and extrusion process. Several machining operations like drilling, grinding, turning, threading, profiling, etc. on all materials, both conducting and non-conducting. Recent development used is, instead of using slurry, the tool is impregnated with diamond dust. In some cases, it is impossible to rotate the tool, so the workpiece will be rotated in some cases. This recent development we will be studying in Unit 5. Thank you.